Imagine for a moment you're tasked with designing something meant to fly at 25 times the speed of sound, or maybe guiding a spacecraft safely back into Earth's atmosphere, facing temperatures, hotter than molten lava. How do you even start? How do you test or understand materials that need to survive conditions like that? Conditions that are often just impossible to replicate here on the ground. Well, today we're taking a deep dive into a really landmark development, something that's fundamentally changing how we simulate and understand these incredibly harsh environments. We're talking about the Center for the Exascale Simulation of Coupled High Enthalpy Fluid Solid Interactions. Thankfully, it's known by a shorter name, CHEFSCI. It's a brand new research center at MIT, and it was specifically chosen by the U.S. Department of Energy's National Nuclear Security Administration, the DOE-NENSA. Now, that name, high enthalpy fluid solid interactions, it sounds complicated, but it basically gets right to the heart of the problem. High enthalpy means gases that are unbelievably hot, moving at extreme speeds, like the superheated plasma you'd find around a hypersonic vehicle. And coupled fluid solid interactions, well, that means they're studying how those intense gases directly affect the solid materials, how they transfer heat, cause erosion, even chemically change the surface. It's like the ultimate collision course between super fast, super hot air and the material trying to withstand it.
That's a great way to put it. It was announced back in September 2025, part of the NNSA's Predictive Science Academic Alliance program, PSAP-4. And SHEFC isn't just about getting bigger computers to run old simulations. It's really a collaborative effort. It brings together MIT's top people in computational science and AI, uh, nanotechnology too. The whole mission is to combine the world's most advanced computational power with a truly multidisciplinary team to predict things that, honestly, we once thought were impossible to predict.
Okay, so ChefSci is giving us a kind of digital crystal ball, a way to test designs for, say, hypersonic vehicles or next-gen reusable spacecraft without actually building them first.
In a way, yes. It lets us explore possibilities much faster and safer than physical testing alone would allow.
So we're about to unpack how scientists are using these exascale supercomputers and cutting-edge AI, simulating conditions where temperatures go over 1,500 degrees Celsius and speeds hit Mach 25. This sounds really fascinating. Let's start with the basics, though. What makes these extreme environments so, well, extreme? And why are they so incredibly hard to study? What's the real roadblock?
The fundamental barrier is just the sheer scale of the physics involved. You mentioned the numbers, the temperature soaring above 1,500 Celsius, speeds up to Mach 25. That's 25 times the speed of sound. I mean, just to give you a sense, Mach 25 could get you across the continental U.S. in less than 10 minutes.
Wow.
So these aren't just difficult conditions to create in a lab. They're often completely impossible to replicate accurately or even safely. You can't just stick a piece of material in a normal wind tunnel and expect it to survive those stresses, let alone get good data back. The environment itself would likely vaporize most of your sensors, your test equipment.
Right. The test itself destroys the test setup. So if you can't easily test them physically, what are the real-world stakes? Why is understanding this so critical for future tech or, say, national security?
Oh, the stakes are incredibly high. The implications are huge. This research feeds directly into designing the next generation of thermal protection systems. Think about the heat shield on a spacecraft re-entering the atmosphere. That material has to withstand these conditions without failing. Failure means mission loss, potential loss of life.
Absolutely.
It's also crucial for reusable spacecraft. They need to endure these stresses over and over again without needing massive repairs every single time. That's key to making space access cheaper and more routine. And then, of course, there are advanced defense applications, things like hypersonic vehicles, reconnaissance platforms. Survivability and performance in those extreme flight regimes are absolutely paramount.
And it sounds like it's not just about the raw heat or the sheer speed. You mentioned these complex interactions happening right at the surface.
Exactly. At those temperatures and speeds, the surface of a material becomes, well, you called it a battleground earlier, and that's pretty accurate. There are incredibly complex things happening constantly. SHEFC aims to capture these phenomena that really dictate whether a material survives and performs. Things like oxidation, the material reacting with oxygen, basically burning or rusting super fast. Nitridation, which is similar reactions but with nitrogen from the air. Then there's ablation, where the material itself erodes or vaporizes from the intense heat, kind of like a sacrificial shield burning away.
Okay.
And finally, fracture the material just breaking down mechanically under the immense stresses. And the key thing is, all of these happen at the same time, and they all influence each other. It's incredibly complex to predict without these kinds of advanced simulations.
So, yeah, can't easily test physically. The interactions are incredibly complex. You mentioned exascale computing earlier. That sounds honestly like something out of science fiction. For most of us, what does exascale actually mean in practice? How does it help solve these seemingly impossible problems? Is it just faster computing or is it something fundamentally different?
It's It's fundamentally different. Exascale represents a truly massive leap in computing power. We're talking about machines capable of performing more than a quintillion calculations every single second.
Quintillion, that's a billion billion, right?
Exactly, 10 to the power of 18. It's hard to wrap your head around. Think of it this way. If every single person on Earth did one calculation per second, it would take them over 4 years just to match what an exascale computer does in 1 second.
That's staggering.
And that level of raw power isn't just about doing old calculations faster. It allows for simulations with such extraordinary detail, such fidelity, that we can capture the intricate dance between the gas molecules and the solid material at the atomic level, the molecular level, and the larger continuum level, all simultaneously. It's almost like discovering new physics, because we can finally see these interactions happening in enough detail. It changes how we approach material failure, how we design for these environments.
Wow, okay. A quintillion calculations.
Hmm.
But even with that kind of horsepower, you still need the right software, the right approaches to make sense of it all, right? It's not
Yeah,
just plug and play.
precisely. Raw power isn't enough. To actually use Exascale effectively, Chef C is developing brand new algorithms. These are specifically designed for these massively parallel machines where calculations happen across thousands, even millions of processors at once. Imagine trying to conduct a giant orchestra where every musician plays a different complex part, but they all need to be perfectly synchronized. Our algorithms are like that superconductor, managing the complex interplay between fluid dynamics, heat transfer, chemical reactions, and the solid materials response. They ensure everything works together efficiently and accurately at this enormous scale.
That makes sense. So incredible machines, sophisticated algorithms. But even then, simulating everything from first principles must take ages, right? Is there a smarter way? Maybe using AI.
Absolutely. That's the other crucial piece,
Yeah.
integrating artificial intelligence and machine learning. It's
Yeah.
a key innovation here. Chef Sai uses what are called AI-based surrogate models. Think of them as like highly trained stand-ins or shortcuts.
Okay.
These AI models are trained on huge amounts of data, both from the high-fidelity simulations we run and from actual physical experiments. They learn the underlying patterns, the cause and effect relationships. Once trained, these surrogate models can make predictions much, much faster than running the full simulation every time. They allow us to rapidly explore different design possibilities, test different material combinations.
So they learn from the big simulations and then give you quick answers for similar problems.
Exactly. It lets us explore the parameter space much more broadly and quickly. And sometimes they can even predict behaviors in situations we haven't explicitly simulated or tested, opening up new design pathways. It significantly accelerates the discovery process compared to just relying on the full-scale simulations or physical tests alone. These tools even lead to what they call decision engines, helping researchers figure out the best combination of models to use for a specific prediction task.
So it's not just big computers and clever AI, it's also clearly a huge team effort. What kinds of expertise does Chefsy actually bring together? It sounds like you need a bit of everything.
You really do. It's a truly multidisciplinary symphony. They draw on deep expertise from aeronautics, obviously, material science, mechanical engineering, applied mathematics, and computer science.
Quite a range.
Yeah, and this breadth is absolutely essential. These problems don't fit neatly into one box. They're complex, messy challenges that span physics and engineering. You really need all those different perspectives just to frame the questions correctly, let alone find the answers.
That makes perfect sense. And you mentioned earlier simulating things from the atomic level up to the engineering scale. How do they actually bridge that enormous gap? How do you connect atoms to airplane wings, essentially?
Right. That's the challenge of multi-scale simulation, and it's one of Chessie's core focuses. They're developing ways to resolve the structure and interactions right down at the atomic scale, using quantum mechanics simulations to see how individual atoms bond and react at interfaces. But crucially, they link that tiny scale behavior to the engineering scale conditions, the overall heat load, the mechanical stresses, the chemical environment acting on a whole component.
How do they connect those?
They're building a unified simulation framework. Think of it like a universal translator plus a master controller. It allows models describing different physics, fluid flow, heat, chemistry, material strength, operating at different scales to talk to each other and influence each other within a single simulation. It's about coupling these phenomena correctly, So the atomic details inform the large-scale performance and vice versa. Bridging that gap is key.
That sounds incredibly complex but powerful. Are they focusing this power on any specific types of materials that show promise for these extreme jobs?
Yes, definitely. There's a strong focus on advanced ceramics, particularly diborides, materials like hafnium diboride, HFB, and zirconium diboride, ZRB. These are really attractive for hypersonic applications because they have incredibly high melting points, thousands of degrees Celsius.
Okay.
But they do have challenges, especially with oxidation resistance when things get really hot and fast. So Shefty is also exploring what are called high-entropy alloys of these diborides.
High entropy alloys, what does that mean?
It's basically like creating a sophisticated cocktail mix of several different elements within the diboride structure.
Hmm.
Instead of just two main elements, you might have five or more mixed together in roughly equal amounts. The idea is that this disorder at the atomic level can sometimes lead to surprisingly beneficial properties, maybe even better temperature resistance, better resistance to oxidation, or improved mechanical strength compared to the simpler compounds.
So designing materials almost atom by atom for specific superpowers.
Exactly. Engineering materials specifically to survive those hellish conditions.
Okay, these simulations, the multi-scale modeling, the AI, it all sounds incredibly powerful, almost like magic. But
Yeah.
how do we actually know the results are right? How do you trust what the computer spits out, especially when, as you said, lab testing is so difficult?
That's an absolutely critical question. And the answer is experimental validation. It's a cornerstone of the whole Chefsy strategy. These groundbreaking simulations aren't developed in isolation. They rely heavily on carefully designed, highly specialized in-house experiments.
So they do physical tests.
Yes, but maybe not trying to replicate full Mach 25 re-entry in a small lab. Instead, they create specific controlled conditions that test aspects of the extreme environment. For example, they might have facilities that can generate very high heat fluxes, or specific chemical environments or controlled impacts. This provides crucial real-world data points. This empirical data is used to validate the computational models, to refine them, to make sure they're capturing the physics correctly. It's a constant feedback loop. Simulate, test, refine the simulation, test again.
Building confidence step by step.
Exactly. It ensures the models accurately reflect reality, giving us confidence in their predictions, even when we extrapolate to conditions we can't fully replicate experimentally.
And it's not just about getting a single yes or no answer from the simulation, right? It's about understanding the confidence level.
Precisely. That brings in another vital component, uncertainty quantification, or UQ. It's deeply woven into Chefsy's approach. UQ recognizes that there are always uncertainties in complex systems, slight variations in the material's composition, imperfections in the computer model, uncertainties in the operating conditions.
Real-world messiness.
Right. UQ methods allow them to systematically account for these uncertainties and quantify their impact on the final prediction. So instead of just saying, this material will survive, they can say, this material will survive with a 95% probability under this range of conditions, and they can identify which uncertainties had the biggest impact. It leads to much more robust and reliable predictions for decision-making.
And this isn't just happening within MIT's walls, is it? You mentioned the NNSA funding. Are they working closely with the national labs?
Oh, absolutely. Collaboration is key. Shefty maintains very close ties and an extensive collaborative network with the Doenza National Laboratories, Lawrence Livermore, Los Alamos, Sandia. These partnerships are vital. They ensure a two-way street for knowledge exchange, for sharing data, for aligning the cutting-edge research directly with pressing national security needs and broader scientific challenges. The labs bring real-world problems and operational experience, while Shefty provides advanced simulation tools and fundamental insights. It's a synergistic relationship.
Makes sense. Now, this kind of really groundbreaking work, it obviously relies on brilliant people. Who are some of the key individuals leading this charge at Shefty?
Well, the director is Professor Raoul Radovitsky. He's an MIT professor, a real expert in computational solid mechanics, multi-scale modeling, dynamic fracture, particularly how materials behave under extreme loads like blast waves or hypersonic flight. He's the one really integrating the high-fidelity physics, the AI, and the exascale computing. Then there are two associate directors, Professor Yusuf Marzouk, who's also co-director of MIT's Center for Computational Science and Engineering, or CCSE. His expertise is crucial on the computational math side, things like statistical inference, that uncertainty quantification we just discussed, and machine learning, making sure the numbers are crunched right and we understand the confidence.
Okay, and the other associate director?
That's Professor Nicholas Hadji Constantinou, also a co-director at CCSE. He's a leader in nanoscale fluid mechanics, using molecular simulation and multiscale methods to understand how fluids behave at the smallest scales, which is critical for understanding those gas-surface interactions. Together, along with a strong operational team, they bring this incredible range of expertise needed to tackle Chef Spee's really ambitious goals.
It's clear the immediate applications in defense and aerospace are huge. But thinking bigger picture, what's the broader impact of Chef C's work likely to be? How might this deep dive into extreme environments affect us all, maybe in ways we don't immediately expect?
Well, the potential impact is really far-reaching. Beyond the crucial national security aspect, the advancements will certainly help enable safer, more reliable, and more efficient reusable spacecraft. That could really open up space exploration and commercialization, but maybe even more broadly, the methods being developed here integrating AI, exascale simulation, UQ, multi-cell modeling, these tools and approaches could revolutionize how we discover and design all sorts of new
Or
materials.
other fields entirely?
Absolutely. Think about designing materials with tailored properties for, say, better energy storage, more powerful, longer-lasting batteries, or perhaps new materials for advanced catalysts, or even innovative biomedical devices. The computational frameworks and the insights gained into complex material behavior are likely to ripple outwards, accelerating progress in many other scientific and engineering domains.
And it's not just about the science being done today, is it? It's also about training the people who will continue this work tomorrow.
That's a huge part of it. Workforce development is deeply embedded in CHEFC's mission. They're actively training graduate students and postdocs, giving them hands-on experience with these state-of-the-art tools and methods. They also have immersive internship programs at the national labs, embedding students in that collaborative environment. This is really crucial for building and sustaining the pipeline of talent the U.S. needs to stay at the forefront of high-performance computing and advanced science and engineering.
And are they trying to make this complex science accessible to others too?
Yes, they have outreach efforts planned, ranging from K-12 programs to engage younger students, right up to postgraduate training. They're planning public talks, workshops, and making resources available online to share the excitement and importance of this work more broadly.
So this deep dive has really shown us how ChefC is right at the cutting edge. They're using exascale power, sophisticated AI, and this truly multidisciplinary approach to understand and design for environments that were once, frankly, unthinkable to simulate. It feels like a major step change.
It really does. It's a watershed moment in computational science, I think, giving us the ability to see and predict phenomena that were previously beyond our grasp. It highlights how powerful tools, when combined with human ingenuity, can tackle problems we used to think were impossible.
Building the future of flight, space travel, and maybe even materials we haven't dreamt of yet, all starting inside a supercomputer.
Precisely.
So thinking about all this, what does it mean for you listening right now? If we can now simulate the brutal conditions of hypersonic flight or atmospheric reentry with this incredible detail and growing confidence, it really makes you wonder, doesn't it? What other impossible challenges in medicine, energy, climate, or anywhere else could we unlock when we combine this kind of computational power with our own ingenuity? What will we manage to see next?